Okay, so welcome everybody. This afternoon, Cesare Di Mauro will give us a short presentation talking about assembly programming and Python. Thank you, Cesare.
Thank you. I'm Cesare Di Mauro. I'm a copy editor for Punti Digitali, which is an Italian technological blog, and I wrote many articles about CPU architectures. And 2 years ago, I had an idea for a new architecture, and since I think that it's a very good idea, I decided to make it a bit more real. And so I show you how I got a software model for my architecture, and I got some numbers. There are problems. Okay. How I came from for this idea? I think that it's because of the geek nature. Geeks are strange people because sometimes they think that the work that others have made isn't cool, it's bad, and at the point on their life they start to write their language and compiler. And they are on operating system and file system. And for very low-level geeks, a new CPU architecture is the dream to come. And they should do this. So they spend a lot of time doing this because they think that they are the coolest guy in the world, and they want to show it. Sometimes it pays, because we have several examples in real life of people that have made their wonderful language, which many of us love and use. And we had other people which wrote a brand new operating system, which are not Unix-based. And there are other guys which are design new microprocessor, which are inside in billions of devices. In this case, I refer to Chuck Peddle, which who designed the 6502 CPU, which you find in Apple II, Apple 1, Apple II, Commodore VIC-20, Commodore 64, and so on. So, but sometimes it's just a dream, because what you think as a geek isn't real. We can make a processor which has such features, because they can be perfect from a geek point of view, but in the real world it doesn't apply, because it's such a beast is too much complicated and doesn't have a real application. But that's because maybe young people makes so much mistakes, and that's one. How is the CPU market? There are a few contenders, because we have many CPU architectures which are just died. We can think about the Alpha from Digital, and others which are survived, but they share just a few market share. I talk about MIPS, PowerPC, and Spark. That's because nowadays we have only two big players which dominates the market, which is ARM and Intel. What is the current status about CPU architectures, and what are the needs for which comes from the market? We know that Intel processors shines when we think about the performance. They give us a great performance, but power efficiency isn't their best, their strong point. Whereas we have an ARM processor which have a very good power efficiency, but performance aren't so much good. And the market demands for mobile devices which every day must be more powerful. They integrate more memory, so in the future it brings 64-bit architectures for mobile device too. But mobile devices still need to consume a few watts because we found them in smartphones and tablets and so on, very little devices. Servers, we know that need so much performance, but the power efficiency is much important too, because servers must be cooled in an efficient way. So, because we have many cores which are packed together, close, and many racks which are packed in the data center. So, power is an important factor even for servers. PC, desktop are between these two things, between mobile and servers, coming from netbook to high-end PC for gaming, for example. But Intel and ARM carry some legacy stuff in their architecture. We know that Intel should support several ISAs from the very old 86, from 286, 386, and the last is x64. Intel processors also must give some complex instructions which works on BCD, which is a very old data format, and has instructions for raising up a stack frame, which is very complex, and also have some instructions which deal with strings and other strange things. And everything comes from the very old processors, which were 8086 and 186. Intel also must support a very old memory model, which is the segmentation, whereas nowadays we have only paging, which is much more flexible and efficient. And last but not least, Intel has many instructions that gives for programmers. ARM isn't that different from Intel, because ARM in its history has made a lot of ISAs. We have the original one, which was the ARM32. I labeled it like that. And then it comes with the thumb and thumb 2 for code density, which was the goal to reach. Then come with the thumb EE and the Jazilla for the Java virtual machine. And the last one, which is was born, is ARM64 for servers. ARM has also some very complex instructions. It seems strange because it's a RISC processor, but it has the possibility to load and store multiple registers, which is a very hard thing to do at the hardware level. And ARM has also many instructions. So in this scenario comes my architecture, which I labeled Next64T. Why this architecture? Because I think that CISC architectures can say more, and they can also be very efficient from the decoding point of view, which right now is the problem which x86 x64 has. And my architecture has a decoding section which is quite comparable to ARM and Thumb 2. in terms of complexity. It gives a very good code density. Code density is an important thing to have to deal. We don't need to talk to think about just performance or power efficiency when we talk about CPU architecture, because having code density is a thing to deal with. And that was so much important that ARM made the thumb2 IIS just to address this problem, the code density. The architecture has also excellent performance. That's because it comes from the x86x64 architecture, which was high performance, bringing a lot of new stuff. And it's very easy to emulate the Intel CPU at about the same speed. It's a problem, for example, for ARM, because the ARM architecture is very different from Intel, and that's a problem if you have to execute all the legacy code. The most important thing, I think, is that this new architecture is source level compatible with x86x64. Why this? Because new architectures needs software to run. So if we can bring the old software and just compile within architecture, we can have a lot of software that can run on it. It's a very important thing. The new architecture has also 32 general purpose registers, up to 128 SIMD registers, and every single SIMD register has a size that goes up to 1024 bits. It can seem strange, but SIMD machines nowadays go for very wide registers to calculate many data at the same time. It also has a smart code padding. What does it mean? If we disassemble the x86 x64 code, we can see that we have many NOP instructions which were used to just pad the code cache to align it to the cache line. It can be made in a much more smart and efficient way than inserting just NOPs in the code flow. Also, the instructions that were used just 1, 2, or 3 arguments can be easily promoted to use 2, 3, or 4 operands, so we can work just like RISC processors in a very efficient way. The architecture is also tough to be scalable from embedded to HPC. What does it mean? It means that if I need an architecture in a version which was for embedded devices, I can cut it using just 32 bits and using only 16 registers in a very simple way. Or I can bring the most from this architecture for HPC servers, for example. But if you have an idea which you think that is good, if you don't prove that it's good, it's just an idea, and that's all. So I need to find a benchmark to compare my architecture with the leading market. So I think this because Next64T is just a rewrite of x86 x64. I take them as a reference, as a benchmark for my architecture. So what I need now is just to write a model for my architecture, and that's where Python came. To show that my architecture is good, I have to set some key points. We know that a CPU core can be split in two parts, the front end and the back end. We have the front end, which fetches instructions from memory, decodes them, and sends them to the back end, which just runs the instructions. If I use the same backend of x86x64, I can just think about the front end. So I have the backend, which is the same of the Intel architecture, and I only need to compare the front end to show that my architecture is good, is best, the best of architectures compared to Intel ones. So I can compare the front ends, and I can compare the decoders. How I can do this? Just I can take the opcode table. I can see the opcode structure and see how it's quite simple to decode compared to the opcode structures of x86 x64. But I need also to complete the work. I need to map every instruction from the x86 x64 to my architecture, and after this I need to collect some stats about my instructions. To do this stuff, I needed an x86 disassembler for Python. I found this Tom3 library, which is an open source project, which is lightweight, simple, fast, and well documented. But it disassembles many instructions at the same time using a buffer. But it was a bit bugged, so I had to fix something, and I also reported them in its tracker. Most of them were fixed, but some stuff is unfixed now. And it supports everything from the Intel side, from the very old architecture to the Lux extensions such as AVX. I made some improvements to this library because I needed other stuff for my project. First, the Python wrapper lacks some constants and functions, so I added them. And then I found that decoding multiple instructions at the same time was inefficient for what I need. So I wrote a couple of functions to do this stuff more efficiently. And I tweaked also the instruction class, which it generates, to get some more useful information. What I need is also a library to disassemble PE binaries. This Tom3 comes with such a tool, which is called dislib.py. It shows some piece of PE information. I added some more, which were very interesting for me. And but it has a drawback. It just disassembles the first instructions it encounters and just stops. So I needed to do a much complex work to get as many as possible instructions disassembled from the stream. How I did it? The first four instructions were the ones that dislib just disassembles and then stops here. How can I disassemble a lot of more instructions? I just keep track of calls and jumps instructions. I get their addresses, so I can have other entry points where I can start to disassemble instructions. How I made it? Okay, I used an array to mark every byte of the code stream, and a queue where I put all the addresses that I found and that need to be disassembled. how it works. When I get an instruction which is disassembled, I mark its bytes as already disassembled. So the next time that I found the same instruction, I just skip this process. When I found a jump or call, I take the address and I put it on a queue, so I can later disassemble the code stream from this. And when I found absolute jumps, arrays, ints, and illegal instruction, I just stop disassembly, because I found a point where I can safely disassemble instructions from there. I need also to collect some instructions, some information for instructions. When I disassemble an instruction, I get its instruction length, its mnemonic, the arguments if there are any, the constant if it's used, and then the addressing mode. I collect some information and generate some stats using the counter class in the collections module. Now I have all the information about the instruction, so I can translate it from x86, x64 to my architecture. I wrote a new module, which I call the next6040.py, entirely from scratch. It's about 3,000 lines, but it's enough to assemble an instruction. It works by converting the addressing mode from the old architecture to my architecture. It tries to pack the constant to an internal format if it's possible, to save some space. And after that, it packs together the opcode, the addressing mode, and the constant to generate the extraction byte stream. Okay, now finally I can get the numbers and compare my architecture with the real world. To do this, I use the Adobe Photoshop CS6, which was released as a public beta 2 years ago, and I use it because it has many extractions that I can decode, each about 1,700,000. Which is enough to get some concrete numbers about the efficiency of my instruction. Unfortunately, for the 32 bits version, my architecture shows a bit more space which is needed to accomplish the same task. So the size is greater than the Intel one. It's not so much, because it's just 6% more space needed, but it's fatter. The things changes completely when I move to 64 bits, because my architecture shows a very interesting result. Globally, I need much less space than the x64 architecture to generate the instruction. So my architecture is much more efficient than the x64. With this data, I think I can explain why I think my architecture is better than x86, x64. Okay, now about Python. All this work wasn't possible without Python, because with Python I had the possibility to write a software model for my architecture in a few times. It let me experiment many ideas which I had in the last 2 years, and I got also I wrote 2 ISS versions of my architecture, and I'm still developing a third one. So thanks to Python, I had the possibility to have some numbers to compare my architecture to the real world. That's all. If you have any question, I can show details about my architecture for because it's my private stuff.
I was interested to see the comparison between the 32 and 64 bits. There was the line with the average instruction
Yeah.
size. I do not understand why do you think it doesn't work for 32 bits? So the instruction size there is 3.2 and increases on for Intel it increases, right? So but why can't you be as small?
That's because my architecture is quite different from the Intel one. So for this case, 32 bits case, it's not as much efficient as the Intel architecture.
Just random things I had on my mind. Did you consider working with, for example, Valgrind, which I think I'm not experienced in the field, but it emulates architectures, and that could be interesting to get Valgrind to run a program, because you're not executing anything now, right? You are just
I just disassemble executable existing.
You do not have actual runtime information.
No, not runtime information. I just translate the instructions from the Intel side to my architecture.
So basically, all you know, you have a higher density of the encoding of the instructions, which is already quite an achievement, because you do not have a compiler which probably could take more advantage of your instruction set.
Yes, it's just a rough translation. So I cannot take care of the improvements that my architecture had. For example, I introduced memory-to-memory instruction, which is much more efficient than the usual load on a register and store to memory, which requires 2 instructions and requires a register that you need to trash just to do this task. With my instruction, you don't need to trash a register, and it's much more efficient, because in just one instruction you do the things that the other architectures requires 2 instructions, and also it doesn't hurt the pipeline, because with the other architectures you have to load the value, and then when you store it, you need to the previous instruction to finish the load before the next one can be executed.
And you didn't compare to ARM, did you?
No, that's because my architecture comes from Intel. Intel is quite much performant than ARM. So Intel is my benchmark, my reference. ARM is important if you think about the power consumption. So I can compare to
many people now. Performance is what you get out of per watt. That's even for the server world. I think you wrote on your slide that the server should be fast, but I think in reality now people are thinking, how much energy do I need to deliver a certain set of instructions? So actually I think that's kind of an obsolete information that you're giving there when you're saying burnout cycles and be fast. That's not the standard. Okay,
but if you think about how Intel spends its energy in decoding instruction, okay, it is where my architecture comes. I cannot show you my opcode structure, the opcode table, but if you might take a look at it, you can see that the extraction format is very, very simple to decode. And this brings to a decoding section which is much smaller. I think so 2 orders magnitude.
You think you improve there? You would make it? It would be lower that then.
Yeah, I improved the decoder because Intel has problems with the decoder, which is very, very complex, requires millions of transistors to achieve the task, and you cannot turn off the decoder in a CPU because instructions need to be fetched, decoded, and executed. Okay. Intel comes with some tricks with the NeHLM architecture, such as using a little buffer for already decoded instructions, so you don't need to decode them every time if you have a very little loop. But it's just a scenario, a case. On every other scenario, you need to decode every time the instruction. So the decoders run every time and draws a lot of power.
And one final question. So you're not making a hybrid thing. You will have a thin layer which allows you to be compatible with the Intel architecture. There's a translation that could also be built in hardware, and then it could be compatible. But you couldn't do that for ARM, because initially it looked like it was a you had something which you could translate ARM into your thing, and you could translate Intel into your thing, and then we would have a processor which can run all the software.
Yes, that's why I've added some features on my architecture, which I haven't talked about it, to improve emulation of other architectures. I think that old ARM32, which uses 16 registers, can be easily emulated by my architecture, as well as the Intel architecture. It's different for ARM64 because ARM64 brings 30 general purpose registers. So I have trouble mapping all the ARM64 registers to my architecture. I have a lot of registers with my architecture. Yeah, 32 general purpose registers are, I think, good enough, like a RISC processor. We can emulate a lot of architectures with this new one, and efficiently, and I think, but not all.
Any other questions? Okay. So thanks again, Cesare.
Thank you.